Hello and welcome to ABE 474, Indoor Environmental Control. This section is going to cover Chapter 6, which is Space Heating Load. And when we say space heating load, what we're really talking about is the amount of heat that needs to be supplied to a space in order to maintain the set point conditions. So in this chapter, we're going to start to put together some of what we've been looking at in the previous chapters. And we'll be combining that with some new information and in order to essentially size our heating equipment. So let's go ahead and get started. First, let's review and kind of build on some of the concepts we've already seen in the past, and let's ask the question, where does our heating load come from? So there are a number of things happening that would require us to provide heat into the space. The first one pertaining to the heat transfer, which we saw just in the previous chapter. So heat loss or heat transfer through the structure or through the building envelope. And another would be the air that we're bringing in may be cooler than the temperature that we're wanting to maintain our conditions, so it could reduce the temperature in our space. So we might need to supply some heat to offset that. So outdoor air that we're bringing in through our ventilation process. And something that we haven't talked much about to this point, leakage. So unintended air that's coming in, which is a form of ventilation, but it's not the ventilation that we are controlling. And so this leakage we call infiltration. And so what causes infiltration? This is our new concept we're going to also work with in this chapter. So what causes infiltration, or what causes this leakage? And it's primarily, we can break it down into, it's being caused by the fact that we have cracks in our structure or cracks in our building. And those allow for air to pass through them, but you need a driving force for that. So the cracks allow for the movement, but you need the driving force, which in our case has to do with differences in pressure. That's what causes air to move from one place to another, is some differential, some driving force, a difference in pressure. And in the case of our structures, the driving force for the air to move, get ahead of myself here, the driving force that's creating this pressure could be from wind that's outside the building, or stack pressure. It could also be related to pressurization of the building by our ventilation system. But the wind outside and the stack pressure are two that we have less control over. So we're going to look at those and what causes them and how much leakage do they result in. But first, we're going to continue on our kind of process that we normally go through. We're going to first look at a little bit of vocabulary. So making sure that we know some of the terms that we're going to be using. So vocabulary, the word fenestration. We have seen this already, but let's review. So when we're talking about a fenestration, typically talking about windows, and in some cases we could be talking about doors also. Windward. When we use the word windward, we're talking about the direction from which the wind blows. And leeward, which is the opposite of windward. It's the direction to which the wind blows. And if we want to kind of sketch it to reinforce what that means, if our wind is blowing from left to right on our page here, then the windward side of the building is the building that's essentially facing the wind, and our leeward side of the building is the side of the building that's opposite the wind. Alright, so moving along with kind of understanding why we're doing what we're doing in this chapter. Why do we need to know the heating load? We already covered it, but let's just, say it again to reiterate and lay out our thoughts in a logical fashion here. So why do we need to know the heating load? Because we want to estimate the maximum probable heat loss from a space. Why do we want this? Why do we want the maximum probable heat loss? Because we're going to use this information in order to size our heating equipment. And we want to make sure that our heating equipment is able to operate at the most extreme conditions, which is why we're estimating the maximum heating load. So essentially we want to make sure that we're choosing equipment properly. Okay, so let's move on to talk about how we're going to figure out. So we know now we know where it comes from and why do we need to know it. So how do we estimate it? So we'll start with just simply the heating load is the sum of all of the heat losses. So essentially, if you want to maintain set point in a space, you know that you're losing heat, you need to supply as much heat as is being lost to maintain a steady state condition. And so we already said that those heat losses could come from heat that's transmitted through the building envelope, plus the amount that is required to warm the air that's being brought in. Okay. The heat loss throughout the day and throughout the week and throughout the year is going to be transient. So this heat loss isn't going to be a steady heat loss all of the time. So we need to be aware of that as we're analyzing this scenario. So it's important to note that heat loss is transient. So if we're looking for maximum heat loss, we want to bear that in mind to make sure that the conditions that we're selecting for are reasonable to give us the conditions that are going to result in the maximum requirements of our system. And so this transient can be related to the outdoor temperature, which changes throughout the day, throughout the week, throughout the year, the velocity of the wind against the building, as well as sunlight. And so all of these things are going to be changing over time, which gives us a transient heat loss. But for the sake of being able to do these calculations, we are going to make an assumption that we are at steady state. And the reason that this is okay in this scenario and why it works in this scenario for what we're doing in this class is because we're going to be looking at heating load is going to be the most significant in winter, and during winter conditions we actually have the most stable, steady conditions. So that's one of the reasons why it works. And then also we're going to make the assumption that our heat loss is going to be at a peak. During the early morning hours, so just as we're going from nighttime to daytime. And there is rationale for that as well. That I'm not going to spend much time on in this lecture, but feel free to look it up in terms of when you're going to have the most loss to the sky and when you're going to have the coolest temperatures outside is typically at the time when we're at the end of night and just transitioning into the day. All right, so if we wanted to do a more sophisticated analysis, we would need to do a transient analysis. And so depending on your situation, you may find that the steady state assumption is insufficient. For the purposes of this class, we're going to do a steady state assumption. But if depending on your scenario, as you start to develop some intuition in this area, you may find that you need to do a transient analysis. And so you may need to do a simulation study. And if your simulation studies need to include solar effects, so if you're in a scenario where you know the solar effect is significant, then you're going to need to do this transient analysis. And if you recall, we talked about light structures and massive structures a while back, and so depending on the type of structure and the scenario and what your application is, the steady state assumption may not hold. For the purposes of our class, we are going to use the steady state assumption. All right. So in order to do our calculations for heat losses, there are a number of pieces of information that we need to factor in. So first, let's start with different design conditions that we may need to apply, and we'll start with outdoor design conditions. And we're typically going to pull these from the weather data that we can get from ASHRAE. It's typically the summary that we'll use, but you can get that also from NOAA in their historical databases as well. Okay, so if our design is going to be based on an extreme weather event, which is going to be winter because this is a heating system, then we're going to end up with a system that has excess capacity most of the time. And there are situations where this trade-off is worth it. And so it really has to do with how often are you comfortable with your system being in a position where it can't provide the set point temperature because of the outdoor conditions. So, for example, if you design your system to provide the set point temperature 95% of the time, then 5% of the year you're not going to be able to maintain those conditions. It doesn't tell you how far away from those conditions you're going to be, but it tells you that you won't have the capacity to operate and get the set point condition that you want. It doesn't mean that all that time is consecutive. It's the accumulation of all the time throughout the year that you won't be able to maintain the set point condition. So depending on your scenario is how often, how much of that time you can tolerate. So typically in residential homes and things, we will tolerate the most amount of time outside of those conditions. And then second most would be things like office spaces and entertainment venues, those sort of things that aren't in some sort of a critical capacity. They're not serving populations that are at risk or anything like that. And then the least tolerant are going to be things like schools, certainly hospitals, where the populations that are being served by those facilities are at a higher risk for complications during the time whenever it's not maintaining the ideal conditions. So if you design your system to be for the most extreme conditions, then a lot of the time you're going to have excess capacity. There are implications of that for efficiency in terms of operating your equipment. If you're not operating at the design condition, so this capacity, you're going to be operating somewhere else on the efficiency curve, which is probably not going to be as efficient. But there are creative solutions to get around that. And the purpose of this class is not to select all the equipment, but just to recognize as you do your analysis what the implications of your choices are. So with that said, let's take a look at kind of an example for selecting this outdoor design condition. So you're going to select it based on where you are, where your design is going to be implemented. And for the sake of this class, we're going to use the tables in your textbook to select the temperature, but you can, like I said, find these updated tables and more complete tables through ASHRAE. And the tables in your book are adapted from ASHRAE. So on page 597, you'll find weather data tables. And we're going to pull off an example from Chicago, which is close to us. And we're going to use the heating design condition. And if you look in that table, so go ahead and pull that up, pause it if you need to, grab your book, pull it up. You have two values that you're looking at here, a 99.6 value and a 99 value. And the dry bulb temperature that you're given is -6 or -1. So what that information is telling you, same thing on the cooling side, but in this section we're only going to look at the heating, not values. But essentially, this is a very poorly drawn normal distribution curve, and our weather conditions, this would be the average weather condition, the median weather condition. These are all the temperature occurrences above that and all the temperature occurrences below that. And then you have a 0.4% or a 1% value at the bottom. And up at the top you would have a 99.6 or a 99% value. And what these are telling you, so this would be for the cooling load, and this is going to be for the heating load, so for what we're looking at now. Essentially, this 99.6% value says that 99.6% of the time the temperature is going to be above -6 Fahrenheit. So if you design your conditions to be at -6 Fahrenheit, then 0.4% of your time the outdoor condition is going to be such that your system can't maintain the set point condition that you have selected. So 0.4% of the time your system will fail. And how much it fails or how significant is the failure, well, it depends on how far down you are here, right? And then similarly, if you choose the 99% value, it's -1, which is going to be just up a little bit higher, meaning that you're going to be in a failure mode a little bit more. But the difference in design conditions between these two can be significant for selecting your equipment, for operating the equipment. And so that's why those two values exist. So let's kind of put it in perspective with a little example. So there are 8,760 hours per year. And if you chose the 0.4% value, then it means that 35 hours out of the year you will have conditions that are that are more severe than your system can cope with, and so you'll be outside of your set point temperature. And if you go for the 1% value, it is 87.6 hours per year that you'll be outside of that condition. So that's a little bit about selecting your outdoor design condition. So up until this point, I've given you an outdoor design condition for all of our problems in class. And so that is one way to get a design condition, depending on, sort of when you're ready to select and size your equipment. All right, so now let's take a look at indoor design conditions. And we're not going to spend much time on this because we covered this. We talked about comfort of the occupants. That was in chapter 4. And we also did heat loss calculations. And so both of those should factor into indoor design conditions. And you select those indoor design conditions. And one strategy is to balance comfort of the individual and energy use. Just kind of rule of thumb, typical values that we use: 20 to 22 degrees Celsius, or 68 to 72 Fahrenheit. And those are typical values that we use for humans. And if your occupant is not a human, then you need to look it up. So for animals, for plants, for microbes, for processes, for whatever it is that you're working with. But these are just examples for humans. All right. And then the next thing we need to look at are the building transmission losses. And we just covered that in the previous chapter, so we're not going to spend a whole lot of time on that as well. We covered that in chapter 5. But if you recall, your heat loss is related to the heat transfer coefficient of your building, so the overall heat transfer coefficient of your structure, times the surface area of that structure, times the difference in temperature between inside and outside. And then the last piece we need in order to calculate our heating load is this piece that I introduced at the beginning of this section called infiltration. So let's spend a little bit of time thinking about infiltration, and that will wrap up the first part of this section up to the chapter 6 section, and then we'll carry on with the second section estimating this infiltration. But let's see, so we have our control space. And I'm just going to represent our occupants as some sort of a black box, but contributing some sensible heat load. We have an indoor temperature. We have some mass of air that we're bringing in. Okay. And our outside temperature, because we're calculating for heating load, is going to be cold, dry air outside. All right. And then this is the massive outdoor air that's coming in that's not a part of the ventilation air. So I'm not sure if I misspoke about that. But so this air that's coming in, this is our infiltration air. So the sensible heat supplied, and so this may be from our animals or this may be from a heater that we're including, and so that's really kind of what we're saying here, is this amount of energy supplied needs to be sufficient to offset that. So the amount of energy supplied, which could be by occupants or by the heating system that we select, The amount that's required due to infiltration is related to the mass of air that's infiltrating into the space times the properties of the air, much as we've seen before. We've seen this equation before. But just to show that we're following in that same thought process, we're revisiting it. So just a few notes about this equation. If you're going to do it on a volume basis, you want to make sure that you're looking at it for the outdoor condition. And in order to do your estimates, there are two methods, primary methods, for what's the word here? For estimating air infiltration in building structures. So there are ways to actually test this. So in a residential housing, we can do things like a blower door test. In some of our larger animal facilities, if it was really critical to get this, we could do something like a concentration decay test. So injecting a gas, bringing it to steady state, and then watching how the concentration falls off over time can tell us how much ventilation air is coming in. But there are two calculation methods that don't require any measurements, any actual in-person measurements, but they're ways to get rough estimates. Okay. So one is called the crack method, which is classy. It's very literal, but put in the context of pop culture, it could be the butt of many jokes. And it's based on our structure and the characteristics of that structure and the components, as well as the differential pressure between the inside and the outside. The other method is called the air change method. I just want to call it the air exchange method. It's the air change method. And in this case, you assume some value for the air changes per hour. Excuse me. That's more based on experiences and less based on physics and physical properties. We're going to stop this first part of the section on Chapter 6 here, and we'll pick back up where we start to look at these two estimation methods and then wrap up the discussion about space heating load and the amount of heat required to maintain set point conditions in a space.